This discussion relates to a piece of work that went on for 2 or 3 years, and it started off originally as a problem of diagramming building context diagrams for large enterprises that were changing technologies. So I'll speak mostly about a retail bank here, or retail banking. Most banks have hundreds of applications. I've seen up to 600 in a few sites. The technology stack is endless. Everything from COBOL machine code to the latest thing that's washed up on the beach. So there's a large range of technologies around, and lots of integrations or interactions between these applications. Many of them are redundant just because of the way application development is done. And there's huge differences in the available documentation. So in order to model these things, you need to build some form of common denominator to record these interactions. Okay, successful transformations are staged. A big swap out only works in a small landscape or an extremely well documented landscape. So we have to do it piece by piece. And the core of this discussion is, how do we model different approaches to transformation? And what I mean by different approaches is primarily when do we coexist applications together, and when do we decommission applications? So these are the two biggest decisions you make in a transformation, but there's large implications between the integrations. Okay, so I'm going to use some Archimate terms. Archimate's a open group standard for modeling enterprise applications. So there's always a great discussion as to what an application is, or an application component. For the purposes here, I really mean something that can run by itself, and that in a containerized environment, an application can be a more complicated discussion, but legacy environments are normally quite clear. An association relationship within this Archimate scale is the most simple generic directional relationship that you can have. So we'll use the lowest common denominator. Plateau is a useful term. As I said at the beginning, transformation needs to be staged. Archimate has this idea of a stable architecture, but not a permanent architecture. So it's like a step towards a target. Work package, so again, a set of actions that are intended to produce something, and the deliverables, and the something is the deliverable. So a plateau is created by multiple work packages which contain multiple deliverables. And then the rules are this is not part of Archimate. This is what's being modeled in Neo4j. These are the set of actions to be applied from one plateau to get to the next. Okay, so if all the documentation in an enterprise looked like this, the world would be great. It doesn't. So here's an example from Bayern, which is a retail banking organization set of standards that is both a classification and a service-based set of definitions. So if we just look at that, this would be, in the model we're discussing, this would be approximately 10 interactions. And if we just looked at that update customer credit rating action itself, would be another sequence diagram below there saying what happens if we get a failure, what happens if there's a technical failure or a business failure. However, for the purpose of modeling at the enterprise level, we ignore the level below this. So this is 10. So if we use a simplified environment, this is what about 20% of a large enterprise looks like. The red are the synchronous online transactions, and the green lines represent batch. This is just a simulated data generated from a real masked data, if you like. So you can see there's large numbers of interactions between the applications, and when we change one, what happens next? So that's how we would use Neo to model the implications. So let's look within Neo. We're gonna say that the application components are nodes and the interactions are relationships. Because we're using a directional model, and obviously relationships only go one way. For synchronous or online, we read the line as gets data or updates. And for batch, batch or messages, where the provider of the data is sending a file or a message to the consumer, we say gets data from. So you still read the arrow in one direction. And every relationship needs an integration pattern, which is the thing we're going to transform. And so you need a custom attribute plus any other information that's of interest to a particular site. So let's look at this as an example. Let's say application one communicates via it can be anything, a REST gateway to a SOA model, which then communicates with the application B. So this is how you would, this is physically what something might look like. If we use use that pattern term, we see it as A has a pattern relationship with B, and then let's label it as saying that the gateway is a G, the SOA layer is S, and the second gateway is G. So again, GSG is just the label on this particular model here, and you make those single labels site-specific. So I've seen integration patterns that are up to 7 letters, believe it or not, seven letters. And as I said at the beginning, if you have a very detailed inventory, you can always reduce it to this level of labeling. If you don't have this, if you don't have a proper inventory, at least the application teams can capture this information at the level of a label, providing they're given sufficient help. Okay, so let's look at a simple transformation. This is an asynchronous batch relationship between a provider and a consumer. So the provider sends a data object, a file, for example, to the consumer. So that's physically what it would look like. In the inventory representation, you would see that the consumer has a gets from direct relationship with the provider. We're going to transform this to a data hub, which is a normal model to say, stop sending, get rid of all the point-to-point file interfaces, put everything in a data mart or a data hub, and get a consolidated set of information from golden sources of each of the data providers. So this is, again, physically what it would look like, and then we would represent it in the inventory or plateau state with a new interaction ID and a new pattern. So what we're really interested in modeling is the changes in relationships between consumers and providers and the changes in patterns. Okay, go back to the plateau idea. So under Archie made the definition is a stable architecture for a limited period of time. We have in this picture, we're saying we're baseline and we want to get to plateau 4. So obviously getting to plateau 4 in one jump would look best on paper and would be the cheapest possible solution if you were to cost it as a project manager. The problem is it doesn't work. And I think anyone who looks through endless discussions of large enterprise integration projects, most of them fail either because they don't make they never make budget, they never make time, and often I think something like 40% are cancelled completely. So multiple plateaus generate incremental deliverables, but they're more likely to work, but there's a cost. but there's a clear cost up front. In a single step, you hide the costs, or you're not aware of them. So with a plateau, you have longer timelines, coexistence. That means you have to make enhancements to apps that'll be decommissioned, duplicate interactions, and regression testing. Again, so quickly, to reiterate what I said at the beginning, a plateau is created from a series of work packages, and under the work packages are deliverables. So let's forget the model. This is the more formal model of that on the right. Okay, again, you can see this is using Archimate standards, which is very similar to UML, except they reverse where the diamonds go on the composition and aggregation. But you can get an idea of how we're going to calculate the total effort, because what we're going to do is evaluate different transformation options and then look at the costs, the estimated costs of these things. Okay, so here are some of the rules that we're interested in, and this is a subset to make it clear. Decom, that means get rid of the application and all its relationships. Delete relationships, that means remove everything between these two keys, or in the slide, app 1 and app 2. Again, we build a plateau through a series of rules that are applied to the current state of the network, and coexist is probably one of the more useful things. It says if I give you a new application, duplicate all the interactions between the new application and those in the old application list. So it creates a parallel run scenario. Merge similar integrations is a method of removing redundant interactions. So this requires you to build a key or a composite field which tells you what would it mean for an application to be duplicating an interaction. And you mostly see this in batch. So if it's the same consumer provider, same pattern, same data object, same details, whether it's a financial or a non-financial transaction in finance or some other attribute, then you probably are duplicating a interaction. This is very common in batch, and replaces obviously a coexistence followed by a decom. So these are some rules that you can put together to build. So this is the general approach. So we have the code we wrote was in Python, and we need some feeds, and they can be coming. If it's the application inventory, this can be a portfolio system. It can be an Excel. Many organizations keep their application portfolio in Excel, so you can take a subset from there. It's not strictly necessary. All it's strictly necessary for is the applications that don't yet exist, because if they already exist, then they'll be in the interaction inventory, at least at a label name. If you don't need to know anything more than that, then more than the application ID, then the interaction inventory is sufficient. So the key part here is the interaction inventory. So we need a unique ID, and it has to be created, and then the consumer and the provider details, and the integration pattern code. All the other stuff is additional, but useful for understanding what's happening. And then you have to determine what the cost estimates are. Action to decommission, coexist. These are arbitrary effort amounts, any units you like. So the action, there's a cost against each time you do it. And then there's the pattern transformations that are allowed. So AD, if I have an AD, it'll go to AH, whatever that means for the Pacific organization with an effort. Okay, and the key part is the plateau rules here. So this is just showing actions to create pattern 1.1, and we see coexist the 999 very old system with these two legacy systems. So all that would mean that all the interfaces that these old keys have are duplicated to the new 999 application and modernized. So this rule set determines the set of plateaus in a particular approach for transformation. So you are able to generate multiple rule sets by hand and then see what the final costs estimates are of different approaches. So this is the whole rationale behind the discussion. And of course, at each plateau, you can view a context diagram to frighten the management. Okay, so this is the APOC representation, sorry, the something lower detail of what the code would look like. It's probably not worth going through, other than, I guess, the merge and the replace uses some of the APOC codes, so that vastly reduces the amount of Cypher you have to write, but you still have to do a before and after snapshot to do the effort calculations. Okay, so I'll run you through a very simple example here. This is using the data, the Graph Explorer module. So our mission here is to coexist application blue with a red one, and then decommission the blue. So this is what the two rules would look like. So plateau 1, coexist application red with app blue, and it could obviously be a list of apps. So we would run that code, run that rule set in the model, and you'd get something like this. So here you can see that the red now has all the interfaces that the blue had, and there's now also a spreadsheet with the whole interaction inventory generated for that plateau. So we have the as is followed by plateau 1 and the whole interaction view of the enterprise. And then let's execute run plateau 2, and you can see here that the blue is gone because we've decommissioned it. So obviously again you have an exported inventory of what the enterprise looks like and what the integration patterns are and what the work packages look like. So here's a more here we have a scenario that's closer to a real world, where we're starting off with say 100 as is 187 apps, and at plateau 4 we're dropping it to 109, which is a common approach in certainly in retail banking, because they have hundreds of duplicated applications in addition to duplicated interactions. So you can see here we have I'm just highlighting one line, the plateau 1. You can see that we have number of asynchronous interactions, number of synchronous, total number, and then the integration effort, estimate of the integration effort, and the estimation of the app effort. And it's not the full application effort, because there's project management work, there's BA work, and there's business transformation work. We're not attempting to model this. We're modeling the whole the enterprise integration changes. And you can see that on the right, the column shows the number of apps impacted at that particular plateau. So this, to summarize again here, this represents one rule set. You would generate multiple rule sets, and each rule set represents an approach to transformation. And you can probably guess from the model here that the more plateaus you have, the more likely the project is to succeed. However, the more expensive it becomes. So there's an endless trade-off. But at least you can model it in sites where this type of volume of transformation is required. These estimates are done by people in the background typing away all night. Oh, what if we keep this application for another year, or what if we move it into a different phase? This turns into a manual effort using this style of approach with a graphical database. You can model things in minutes. So here, just at the bottom, you can see the effort model. So let's just summarize. This approach was a strategic planning tool for evaluating different EAI approaches. So it's not giving you a full model, but it's giving you a reasonable assessment of the impact of different approaches, and with an estimation model. In addition, it builds the outline of the integration work packages for project plans. So it doesn't tell you anything about the resources you're using. It doesn't really tell you about the timelines. It doesn't tell you anything about the external dependencies, but it builds the actual work packages at the application integration layer. So the model you choose is the one you're going forward with whatever plateaus. It tells you where they fit into the high-level project plan, and the key focus is the talk is really that we are exploiting Neon's ability to manipulate graphs with a few lines of Python rather than working through a database manually. And anyway, so that's about it.